My name is Zan Huang. I am a marketing manager for WooSpeed. Today, I'd like to introduce and showcase WooSpeed's online simulation tool SpeedFit in a simple MPPT boost converter and show how WooSpeed's 1200-volt MOSFET can achieve high efficiency and power density even under elevated temperatures, therefore benefit commercial and industrial solar applications. From the WooSpeed homepage, under the Tools and Support pull-down menu, we can find the SpeedFit design simulator. First, let's choose the topology. Here, we're using the DC-DC topology of boost converter for a typical solar MPPT converter. We choose 400-volt DC input, 850-volt DC output, and 20 kilowatt for a typical commercial solar inverter. The next step is to choose the switching devices, such as the MOSFET and the diode. For the MOSFET, I'm using the 1200-volt 4-pin TO247 4-pin C3M0040 120K, putting two in parallel and using the suggested gate resistors of turn on and turn off for 5 ohm. And for the diode, I'm choosing the 1200-volt 30 amp device C4D30 120H, also two in parallel. In the circuit tab, we can choose the inductors, capacitors, and the switching frequency. Let's start with the given value. The next step is to choose thermal. In the thermal, there are two parts of it. First is the thermal resistance of case to heat sink. Here I'm using the given value of 0.85 for a greased TO247. Please note that this thermal resistance is per device as indicated in this graph. And that means the more devices in parallel, the less equivalent thermal resistance it will have. The next step is to choose the heat sink, whether we use a variable or fixed model. Here I'm using a variable model, and I'm choosing the thermal resistance 0.25. We start with an ambient temperature of 25 degrees C. The SpeedFit is based on Plex and it runs very fast. It shows some typical waveforms such as voltage and current on the right side. On the left side, we can see the efficiency reaches 99.58 in given condition, and temperature of the two devices only reached 80 degrees C and 66.5 degrees C. Showcase that we are running a very efficient and cool circuit in this simulation. Next, let's change the frequency higher. The 20 kHz is a typical frequency that silicon IGBT design would choose. However, with silicon carbide, we can easily up that frequency to much higher and still have efficient conversion. Here I'm using 65 kHz. Keep everything the same, hold the result so we can save it for comparison and simulate again. At 65 kHz, we can see efficiency go down by only 0.2%. While the conduction loss remains the same, switching loss did tripled. However, because the switching loss is so low to start with, the power loss is still low, and temperatures of the device only reach lower than 120 degrees C and 78 degrees C. Still have plenty of margin comparing to the maximum junction temperature allowed for silicon carbide devices, which are 175 degrees C. Next, let's change the thermal conditions. 25 degrees C ambient is ideal. However, in real life, the air temperature can easily reach 40 degrees C and above. And for solar inverters that sit in rooftop, it will be even higher. So here, we're using 55 degrees C as the ambient and see what happens. Hold the result and simulate again. We see efficiency drop only 0.04%, even with 30 degrees C higher temperature. And that's because if you look at the switching loss and conduction loss, only the conduction loss changed a little bit and switching loss remains the same. And that's because silicon carbide has very good performance over temperature, unlike silicon devices. And that gives us a almost flat efficiency curve over temperature. The maximum junction temperature of the MOSFET now reaches 153.7 degrees C, with the diode reaching 110 degrees C. 150 degrees C is typically the thermal limit for silicon devices. However, as silicon carbide has a maximum junction temperature allowed as 175 degrees C, we are still okay with 20 degrees C margin. Furthermore, we can go to change a device if we want to find out. We can use a 1200-volt 32 milliamp device instead, for example, also two in parallel. All the other parameters same. We do the simulation again, hold the result, and simulate. Efficiency went back up to 99.37%, and we can see that's mainly because the conduction loss dropped significantly. In this case, the junction temperature of the MOSFET dropped back to 145 degrees C, showing that with the lower RDS(on) device, now we have more thermal margin for this application. Once you're satisfied with all the simulation results, we can go to the summary side to get a report of all the conditions we have tested and with typical waveforms. You can print or download the report. As a summary, this shows how silicon carbide devices can enable highly efficient, high power density design even under elevated temperature range. I hope you enjoyed this video and find out more by using our online simulation tool SpeedFit. Thank you.